Okay. Thank you very much for inviting me to this anniversary meeting of Indian National Science Academy. It's an honor to be here. What I will talk about is a major discovery in basic science, which is the first observation of gravitational waves, which has very important applications. First of all, it provides means of testing accurately the theory of gravitation that is commonly accepted, which is the Einstein's general relativity. And in addition to this, it provides also a new way of observing the universe, completely different than it was done so far. We are observing the universe by optical telescopes, through X-rays, radio waves, neutrinos, and other means, but this is a new way of exploring the universe. So first, what are gravitational waves? Gravitational waves are solutions of Einstein's equations, and Einstein himself realized this. These are the Einstein's equations. This is the curvature, this is matter. Then linearizing these equations, one gets just a wave equation. And then solving this equation, one finds that the amplitude of the wave to the first approximation is proportional to the second derivative of the quadrupole moment. So in order to have a gravitational wave, you need a non-vanishing time-dependent quadrupole moment. An example of such a system is a binary system, like a binary system of two stars. When they rotate around each other, you can easily convince oneself that the quadrupole moment is non-vanishing and time varying, any derivative is non-zero, and such a system, according to Einstein's theory, should produce gravitational waves. Gravitational waves, they have some properties that are very similar to electromagnetic waves, namely, they propagate with the speed of light. This is the speed of light. And also, like in electromagnetic waves, they have two polarizations. There were, however, over a time, there were some controversies about the existence of gravitational waves. Einstein himself, he linearized his equations and found that they admit gravitational waves in 1916, but in this paper there were certain errors which were corrected in a later paper. But still, in that paper where he derived this quadrupole formula, that the quadrupole is the dominant, there was still a factor of 2, which was eventually fixed by Eddington, who also looked at this problem and had some initially certain doubts, and in one of his work one can see this statement, gravitational wave probably the speed of thought, but really he convinced himself that there are really two independent physical degrees of freedoms, and the gravitational waves are reality. And then later on, Einstein himself wrote a paper with Rosen, saying under this title, "Do gravitations exist?" And he claimed that they do not exist. He considered a cylindrical solution with some singularities, and thought because there are singularities, it's unphysical. But then this paper was criticized by a referee, and there were some discussions, and eventually his assistant, Leopold Infeld, and later on a founder of Polish School of Theoretical Physics, he somehow discussed this with Einstein, convinced him that there was some error in his argument, and Einstein later on, with Rosen, wrote the paper on gravitational radiation. Then, in the late 50s and early 60s, this group of people, Bondi, Pirani, Penrose, Robinson, Sachs, Gaussman, they have shown, studying the full set of Einstein's equations, that gravitation exists, theoretically exists in Einstein's relativity. But some controversies persisted. Namely, Ehlers and others published a paper, and he was criticizing the derivation of the quadruple formula. For him, was not a satisfactory mathematical derivation. It involves some expansions, which are some series, which are where there were no proofs of convergence. But then, in 1974, a binary pulsar was discovered, and then it was shown that the orbit of this binary pulsar shrinks exactly as if the system was emitting gravitational waves according to Einstein's general relativity. And these observations measurements were made, and as you know, awarded a Nobel Prize in 1993. And only in 2015, where a big and complex detectors were built and the sensitivity improved, eventually the gravitational were detected. So, and this was done by the two LIGO detectors almost 100 years after general relativity and almost 100 years after Einstein predicted gravitational radiation. Next are the sources. It turns out that one cannot have a detector with sources produced on Earth, and one need to go to the outer space. And there are numerous sources of gravitational waves that are potentially detectable that originate from the most violent phenomena in the universe. So first, there are the rotating neutron stars, which are rotating and may not be perfectly axisymmetric, and there are various other effects like various instabilities, accretion of matter that can cause a non-vanishing quadruple moment and emission of gravitational radiation. Then there is a primary source, which is a binary system, exactly like a binary neutron star system, which was discovered, and indirectly it appeared to be radiating gravitationally. So in this system, when two stars rotate each other, they emit gravitational radiation. The system loses energy, the orbit shrinks. So you have a signal with orbit shrinks. They move faster and faster, and the gravitational wave is also has higher and higher frequency and high amplitude. So you get a signal, characteristic signal called a chirp with an increasing frequency and amplitude. Then there are other sources. These sources were originally first considered as sources of gravitational waves, namely supernova explosions, which are, it's difficult to imagine that they will be perfectly symmetric, so one can expect a signal. Then a very important type of signal can come from the Big Bang, which can produce a stochastic background, which is also can be detected. So these are the sources. Next thing is the detector. It turned out that the detector capable of detecting gravitational waves is a laser interferometer, which is relatively simple principle, because you have a laser that sends a light. The light is split and goes into the arms, is reflected from these end arms, and then there's an interference which is monitored by the detector. The principle is simple, and this is known to be a very sensitive instrument, but in order for it to detect gravitational waves, it has to be a very big microscopic instrument, with kilometer-long arms. All this has to be enclosed in the vacuum, and this makes it an expensive detector. And on top of it, you need extremely high-quality optics and a very stable laser, and many other techniques like seismic isolation and various isolation from various other sources. So such detectors were built, and now we have a network of detectors. There are several projects. So firstly, there is the LIGO project, which has two interferometers, and there's also an additional smaller detector in Germany. And then there's a Virgo project, which has one such big interferometer. This interferometer started to operate in the early of this century, but initially the sensitivity was not enough. There was a painful process lasting, over 10 years of improving the sensitivity and upgrading them, and eventually the improved so-called advanced detector started to work. And this led to the detection of gravitational waves, something that I will give details later on. There are also other projects. One is the Japanese KAGA project, which is a very ambitious project because it has two important ingredients. One, it is underground, which reduces seismic noise, which is very important, and also on top of it, one will be cooling the mirrors to very low temperatures, like 30 Kelvin. This will reduce the tremor noise. So the construction of the detector was completed, and December this year it will join the network and do the observation. Then there is another detector, which is where construction started. This is called LIGO India. It is called LIGO because LIGO project supplies the optical components, lasers and mirrors, but the detector is funded by India, and India is building this sophisticated, will build this sophisticated long big vacuum system, and of course provide the site, so the construction of the detector started, and the plans are to complete it in 2025. Next slide, I will give a schedule of the observations of these advanced detectors. These observations are divided, they go into observational rounds, which are called O1, O2, O3, O5. So far we had two observational rounds. There was the first one, which was started in September 2015, and soon after it started, the first gravitational signal was detected, something I will talk about. Then there was a second round where Virgo project joined, more signals were detected, and there was also a very significant detection, maybe the signal apparently from the merger of two neutron stars was detected. Now we are in the third observational round. We are in the middle of the third observational round, which will last for 1 year, and I will speak about it at the end of my talk. And here the KAGA detector should join. Then there is the next round planned, which will be O4. Called O4. There will be a break of 20 months with further upgrades. And then there will be another significant upgrade of the detectors, of all the three detectors, and LIGO India should join, and the 4 detectors operate. You see these numbers tell you what is the range, at what distance the detectors can detect signals from the binary neutron stars. This is just the default signal against which the sensitivity of the detector is measured. So you see how it increases. Okay, so we have detectors, and I was announcing we had a detection. So I will now review some most important result. Of course, the most important one is the first detection of gravitational waves, which was done 14th of September by the two LIGO detectors. They both seen the signal, and this was the signal that matched very well a signal from a merger of two black holes. So you see the signal has essentially 3 phases. When they rotate around each other, produce this chirp signal. Then there's a merger, a very sharp impulse, and then apparently the black holes merge from a single black hole that still vibrates and produces the normal modes. And the signal that was observed very well matches the model that was calculated numerically, just by solving full Einstein's equations numerically. So, which is red line, and this is the best model that was extracted from the data. So this was a very significant discovery. It was awarded 2017 Nobel Prize for the three founders of the LIGO project. And the Nobel Prize was, first of all for the construction of the LIGO detector, which was a major experimental achievement, and then, of course, for the observation of gravitational waves. Next important highlight was when the Virgo detector joined. Then, and it happened in August, the three detectors jointly observed a signal, that's from the same source, apparently from binary black hole coalescence. And thanks that the three of them were observing, one could localize the source much more accurately. So this is very important because three detectors provide a fairly accurate position where the source, position of the sky, where this merger originates. And finally, the next extremely important detection was the detection of a signal which apparently originates from a merger of two neutron stars. Here you have this signal in the time frequency plane. So here's the time plus frequency. So you see that there is a signal with the frequency increasing, and this gets stronger and stronger. Okay, and then it goes away. And this signal was detected by the three detectors, two LIGO and one Virgo. But what was also detected, there was an accompanying signal, a gamma ray burst, which happened, around 2 seconds after, and there was a short gamma ray burst. And that was with an extremely high probability associated with this event, and this was extremely important observation because it led to the confirmation that was theoretically predicted that this short gamma ray burst originates from binary black hole mergers. So but this was not all. Here is all sequence of events. The gravitational signal occurred at this time. The gamma ray burst was reported immediately by the Fermi satellite, 2 seconds. It was even before the LIGO apported the signal, just because LIGO needed a few minutes in order to process the data and realize that there was a significant signal. Then the Virgo data was brought in, and the time, and then it was realized, maybe 40 minutes later, that there is an associated with GRE. Observation from the detector produced an accurate sky map, which was revealed 4 hours later, and it was fairly accurate. And then the optical telescope started to look at this sky map, and they found an optical event, a flare, which happened in a certain galaxy. So, because in this region, which was, is fairly small, but still it contains many, many galaxies. In this region, they identified the galaxy where this flare occurred. And this flare was something that is also theoretically predicted, because this was a so-called kilonova event. Namely that, when the two neutron stars merge, neutron stars are formed of neutrons of nuclear matter, then the heavy elements form, and then they decay radioactively, and this radioactive decay gives this optical event called supernova. So that was really a remarkable chain of events that pieced together, the whole and confirmed many theoretical predictions. So really, in this event, it is named by this because it happened 17th of August 2017. And this was the first observation of binary neutron star merger. So this is, of course, the most important. That we have a gravitational wave from binary neutron star merger. Then there is this confirmation of associating with short gamma ray burst. Then, because this electromagnetic and gravitational signal were observed, one could accurately establish that the speed of light is equal to the speed of gravity equals to the speed of light, and an electromagnetic wave. And then there was this kilonova, and kilonova were this heavy element produced, and this explains, origin of certain elements in the universe, because we observe things, for example, things like gold and platinum. These elements cannot be created in the stars due to the stellar evolution, not possible from the physics, nuclear matter physics, atomic physics, and this explains where they come from. The gold that we have is from the binary neutron star mergers, and even on top of it, there was even another very important measurement of cosmological significance. Namely, one could also measure, provide an independent measurement of the Hubble constant, basic cosmological parameter. Here I give briefly, there was the argument that the speed of gravitational waves and speed of light is the same, could be made very simply because the two signals arrive within 2 seconds and from a far away, so we can then easily impose this very impressive bound on the quality of the speed of gravitational wave and speed of light. Then the Hubble constant, the Hubble constant determination was again could be made first of all because from gravitational observation you can measure the luminosity distance. Because of this kilonova event, we identified the galaxy, and from this galaxy one could measure redshift. So given the luminosity distance and redshift, one could provide a Hubble constant. And this is estimation of Hubble constant in gravitational, in this parameter estimation one is Bayesian method. So what one produces is not just the point estimate, but the posterior probability distribution. And this somehow comes between the two independent measurements, whereas you probably know there's some controversy that the measurements from the Planck mission and from the supernova measurements, there is some discrepancy. And the gravitational measure comes somewhere in between. Okay, so here I give just the masses of, these are the masses of the merger events that were measured, okay? So in blue you see the masses altogether during the two observational runs, O1 and O2, 10 signals apparently from binary black hole mergers were measured and 1 from the neutron star. Of course, there are many uncertainties concerning, the ranges of these masses and so on. For example, it's a mystery what really happened, when these two neutron star merged. What happened, whether a black hole is created or some other objects, and it's a bit of a mystery. Okay, so now I go to the third observational run, which is now ongoing. So the run started 1st of April. There was a break in October, and now it's going on. It will end in April. There is a new element here because all the events are made public. So, and this is because that electromagnetic observations can be made, can respond to these observations. There's a question of gamma ray-based kilonova. This is fundamental. Another way, another important thing is that the Krolak detector has joined the consortium. So far, we have 40 observations, which is a lot, because from these two runs we had 11 observations, now we have 40. There are apparently also observations of a merger, which is a black hole and neutron star. There are also certain observations with masses that come outside the ranges of conventionally detected black holes and neutron stars. What we don't have yet in this round is an electromagnetic event. We know with these events, binary neutron stars, binary black holes, binary black hole and neutron star events, one could expect a GRB and perhaps kilonova, but these were not observed. But these events are, well, there are explanations that these events are quite far, much further than the one that was observed initially, and then the gamma ray based beaming. Okay, so now this is the last slide. Okay, just want to mention this is not all. The ground wave detectors are not all. They are planned to send spaceborne detectors. There are also gravitational waves observations made through radio telescope, and also gravitational waves can be measured through in cosmic microwave background. One measures so-called depolarization, which gives some measurements of the stochastic background that originated from the Big Bang. Okay, thank you very much. Sorry.